What is the computational basis in quantum Fourier transform? Imagine trying to understand a secret code that hides the true nature of a quantum state. To decode it, you need to know the language it's written in. That language is called the computational basis. In quantum computing, the computational basis is like the alphabet of the quantum world. It consists of states labeled as 0, 1, and so on, up to n-1, where n equals to raise to the power of the number of qubits. For example, if you have 3 qubits, n is 8, and the basis states go from 000 to 111. These states are just the binary numbers that computers use, but in quantum form. Each basis state represents a specific classical number, and they from the default measurement states in quantum computers. When you prepare a quantum state for the quantum Fourier transform, it starts as a superposition of these basis states. Think of it like a mixture of many different classical numbers combined into one quantum state. The QFT then changes this mixture into a different form called the Fourier basis. This new basis reveals the frequency components of the original state, kind of like turning a sound wave into its musical notes. The process involves mapping the amplitudes of the basis states into phases that encode frequency information. If your initial state is a sum of coefficients times the basis states, the QFT transforms it into a new sum where each coefficient now relates to a frequency component. The importance of the computational basis is that it's the starting point for all quantum operations involving the QFT. It's how quantum information is initially encoded and how it's read out after processing. To implement the QFT in a quantum circuit, you use gates like the Hadamard and controlled phase shift gates. The Hadamard gate, for example, takes a basis state like 0 or 1 and turns it into a superposition, which is essential for building the Fourier transform. These gates manipulate the basis states to produce the desired frequency information. The quantum Fourier transform is a key part of many quantum algorithms. For instance, in Shor's algorithm, it helps find the period of a function, which is vital for factoring large numbers. In quantum phase estimation, it helps determine the eigenvalues of a unitary operator, which is useful in many areas like chemistry and cryptography. Other algorithms in quantum error correction and machine learning also relying on switching between the computational basis and the Fourier basis. So, in simple terms, the computational basis is the set of standard quantum states that representing classical numbers in quantum computers. It's the foundation on which the quantum Fourier transform acts to uncover hidden frequency patterns in quantum data. This basis allows quantum computers to process information in ways that classical computers cannot, making it a fundamental concept in the world of quantum technology.